Hello, everyone. Welcome to this CMCC webinar. And my name is Renato Casagrandi. I'm a professor of ecology at the Department of Electronics, Information and Engineering at Politecnico di Milano. And I will just serve as a moderator for this presentation. And the title of the presentation is Estimating the Impact of Climate Change on Potential Marine Fish Catch. And our presenter is Momme Butenschön. Momme, now you have to help me with your name, Butenschön. Is that correct?
Perfect.
Thank you.
Thank you.
So Momme is a researcher and a modeler now working at CMCC. He has a very interesting path because he started his career as a physics engineer at TU Berlin, then he moved to Stockholm, right, to complete his first part of the studies, and then he came to Italy, in Bologna, where he got a PhD in geophysics. And then from then it started working on the ocean modeling and modeling ecosystems. And since then, now since 10 years or more, he has been working on models about marine science, coordinating the AirSem when he was in the UK, etc., and participated in several H2020 and FP7 projects. Is that correct, Momme?
Yes, thank you.
Good. So could you go to the next slide? Before presenting, his topic, let me spend a couple of words on CMCC. What is CMCC? It's a non-profit organization founded in 2005 that was turned into a foundation in 2015. And the main goal of CMCC is that of studying climate science and its implication to society, to the environment, etc. It is organized as a network of several centers all over Italy in different cities. And go to the next moment, please. The topics. The topics range, from models for agriculture to forests to ecosystems in the oceans, etc. That is why it is organized in several divisions. There are nowadays 8 divisions. And let me mention that, okay, there's the division where Momme is working in, Ocean Modeling Data Simulation, ODA, but there's also a new baby, the Sustainable Earth Modeling Economics, and the acronym is SEME, which is a very fertile word in the Italian language, meaning, seed. So this is the newborn, the new baby of CMCC. I think that's it. So go to the next slide, because the next slide is introducing, the rules of the game. This is not intended to be as a presentation, YouTuber-like, where Momme is talking and one is interacting. There's a question and answer session, so you are very welcome to post your questions. If you look at your monitor on the right bottom side, you will see a question form. You can type your question there. Please enter also your name and affiliation so that we can, first of all, introduce you during the debate, which will be at the end of Momme's presentation. And then in case we don't have time to arrange all the answers, Momme can later on send his personal answers to the questions. So now I give the floor, the cable, to Momme for his webinar now. Thank you, Momme.
Thank you. And hello, everybody. Thanks for joining. I hope you will find the webinar interesting. Today's subject is the estimation of the impact of climate change on potential marine fish catch. I've put my email down here, so in case you want to get in touch after the webinar, just send me an email. Okay. Of course. Okay, now I've got control back. Sorry about that. So the background of this work is it's essentially based on a work that I've done over the last year or so with 2 colleagues, 3 in total. So one is William Chang from University of British Columbia, one is Jörn Bruggemann from the Plymouth Marine Lab, and the other one is me. And we've been working together on this work of estimating the potential fish catch, which has been published recently in June as Chapter 4 in a report organized and published by the FAO, which is on the impacts of climate change on fisheries and aquaculture Census report. You can find it on the link below if you're interested. The whole report, it's a free PDF download, so go and get it. A little bit of overview over the scope of this report. It's a synthesis report, as I said. It has 28 peer-reviewed chapters written by over 90 scientific experts from 20 countries. And it's covering a wider range of topics around the issue. So there's chapters about marine and inland fisheries and aquaculture from global to regional scale. There's mitigation and adaptation strategies, impacts of extreme events, supply and demand evolution, and also the discussion of the climate change poverty nexus. Again, if you want to download it, you're more than welcome to. There's a free PDF download at the FAO webpage. So let's start. The central question of this webinar is, what are the impacts of climate change on the potential fish catch? But there are a couple of other questions that are, I will follow up on from that. And the other two, the main ones that I'm going to tackle is, how does the climate change signal propagate through the food web and affect fish catch? And what role does uncertainty play in there? So if we start from the first element of this central question, which is climate change, the two main pillars of information we have available as a public on climate change is the IPCC, the International Panel for Climate Change, which provides scientific synthesis in a series of regular assessment reports and special reports. So it summarizes the current state of knowledge in science on the subject. And the other initiative is the CMCC initiative, which is a coordinated effort to providing consistent and robust data on climate change from standardized Earth system model projections. So the main scopes of these coordinated efforts are essentially quantifying the climate change as a whole. So how much does the temperature increase? How much does the sea level rise? Global budgets in general, and investigation on the cycling of carbon and nutrients. But increasingly, this is complemented by further investigations of impact at various levels. So what does happen to the ecosystems? What does happen to crops? What is the frequency of extreme events? Are there tipping points and all these kind of issues? The core element to perform these studies are Earth system models, which I'm sure some of you are familiar with. They bring together models for atmospheric physics and chemistry for the ocean, which is sketched in this figure, which I've drawn from a paper from Bonin and Domi, published in Science in 2018. So there's the ocean dynamics as well, with the ocean ecosystem, which we're gonna treat mainly in this talk. And then of course, there's also a land element with a land ecosystem and land hydrology. And these are all put together in one big model that are then run on big high performance computers to provide these projections of what climate change is likely to look like. And these are, the future in these projections is generally phrased in scenarios, so-called scenarios, which are a hypothesis of how the future will evolve, which are usually expressed as different levels of mitigation efforts to reduce greenhouse gas emissions, which in the last cycle of CMIP experiments, CMIP 5, were expressed as representative concentrations in the atmosphere. So let's take a look at climate change in the ocean more specifically. So there's general consensus now on key changes which involve the global warming of ocean and atmosphere, and sea level rise. As I mentioned before, there's a clear evidence of the reduction of the cryosphere, so sea ice melting, and land ice glaciers as well. The oceans by now have absorbed 93% of additional heat and sequestered 30% of emitted anthropogenic carbon. There's an increased occurrence of extreme events like droughts, heat waves, and storms. There's increased stratification. Ocean acidification is increasing by 26% from pre-industrial conditions. There's a decrease in productivity all over across the globe on average, and there's a decrease in oxygenation of the ocean. And also there's observed an alteration of biodiversity patterns because of change of habitats and migration of species due to temperature change. So On a more quantitative picture, there's a considerable spread in the quantity of the anticipated change due to the various sources of uncertainty. This data is from Bopp et al. 2013 for the highest concentration scenario, RCP 8.5, so this is unmitigated change, which states that SST in the ocean is going to increase by 2.73. In brackets, you find the standard deviations of this value across the investigated models. Surface pH is going to decrease by 0.33, oxygen is going to decrease by 3.45, and primary production is going to percent, and primary production is going to decrease by 8.6% according to this study. So if we look a little bit further from these physical biogeochemical variables, what does that mean for the actual ecosystem? There have been studies on that as well. And this is a synthesis from Gattuso et al., published 2015 in Science on a very high level, looking at different components of the ecosystem and ecosystem services and how they are going to be affected, and attributing levels of risk according to literature to these elements. And you can see there's various levels of risks according to the scenario. Again, on the left-hand side, you have the the most mitigated scenario, RCP 2.6. And on the right-hand side, you have the unmitigated again that we've seen before in the data of Bopp et al. And you can see that the levels of risk are significantly increasing with the non-mitigation level. So you see, for instance, for seagrass, which is important as a factor of blue growth for carbon sequestration, and also as reducing the risk of coastal erosion, the same as mangroves. And for seagrass, the risk is very high. You have a very high risk for warm water corals. For pteropods, you have a very high risk, which are an important link in the marine food chain between lower and higher trophic levels, and they are strongly affected by acidification because they can't build their shells. Similarly, bivalves, and again, very high risk for krill and finfish. And this has obvious impacts then on ecosystem services like open ocean, carbon uptake, coastal protection, coral reef recreation, bivalve fisheries, aquaculture, and finfish fisheries at different latitudes to different degrees, but the risk is generally quite high for the unmitigated conditions. So we're gonna concentrate here on what happens to fisheries. And the aim of the work that we were building was to estimate the impact of climate change on potential fish catch, and to give a comprehensive overview across the globe on what's happening to fish catch. And this information is from a lot of studies, often given at a very macro scale level, which is less relevant to policy, which is usually concentrating on the national and regional level. So, for example, you can't build a coastal policy in a very coastal area that it maybe is even affected highly by rivers, on the fact that globally the primary production is decreasing, because in that very area, due to eutrophication, it might be even increasing. And then if you do mitigation policies to increase production, you actually create a problem instead of solving one. So it is important to have this information at a regional level, and that was one of our goals. And at the same time, the large-scale models have difficulties in resolving the regional processes and the coastal processes. So ideally, you would have wanted to perform a study based on downscale simulations. However, these simulations are not readily available in the same extent as the global simulations. So if you at the same time want to constrain uncertainty, you can't, because you usually don't have enough simulations to cover that. And also there's not downscale simulations available for all different regions of the globe. So for our study design, we went back to the CMIP5 archive and used global climate model, global Earth system models. And we coupled these to what is called living marine resource models. So living marine resource models represent the marine ecosystem dynamics and the change in environmental conditions. in this case with a focus on fisheries or on fish. And as I said, the environmental conditions we were taking from CMIP5 projections, we were taking an ensemble of these, so a different set of ESMs available in the archive that drove two different living marine resource models for the projection of potential fisheries catch. All that to get a feeling for the uncertainty in the projections and in our results. To get also a range of response to different levels of mitigation, we use two different scenarios. One is the RCP 8.5 aforementioned, which is unmitigated, and another one is the RCP 2.6, which is the mitigated one. And then we provided individual data for each exclusive economic zone of the world. So on the lower side of this slide, on the lower end of the slide, you're going to find two diagrams of the two different models we applied. One is a dynamic size spectrum model, and one is a dynamic bioclimatic envelope model. And we're going to take a look in a second what these two are. But first, let's take a look at our target variable. So the target variable, as I said in the title, is potential fish catch. What is potential fish catch? So if we look at this graph where we have catch on the y-axis and then time on the x-axis, we can see two different curves. One is a sketch of the potential fish catch, which is blue, and one is the realized catch, which is red. So what actually boats are bringing to land, let's say. So the difference between the two is that the realized catch is the actual level of fishing, while the potential catch is the exploitation at an ideal maximum sustainable yield level in relation to the productivity. So it's the maximum that the system can live with in a sustainable way. So in the long term, the realized catch cannot exceed the maximum potential catch, because that would be unsustainable and the stocks would collapse. However, it may exceed temporarily, which would then be moments of unsustainable fishing that need to be recovered. At the same time, if the realized catch is under the catch potential, that means, or far way under the catch potential, that means that the fisheries is not well managed because it could be used more. And so the distance between the two curves is an indicator also for the efficiency of the fisheries management. So let's take a look at the two models that we have involved in this study. The first one, the dynamic size spectrum model. This one is based on simple relationships between size and abundance, as sketched on the right-hand side. On the x-axis, you have body mass in this sketch. On the y-axis, you have abundance, and it's based on the fact that small organisms tend to be much more numerous than big organisms. And there is clear scaling relationships that are available in from different sources in literature, in science, for all sorts of physiological processes, mortality, growth, and so on. And these type of models use these relationships to project the evolution, the trophic cascade through the marine food web. So it describes populations as density spectrum per unit mass. In this case, we are looking at the pelagic fish community, represented by 100 different log-based weight classes and spanning weights from 1 milligram to 100 kilogram. Fish feed according to size-based rules, as I said, preferring prey generally in optimum 100 times smaller in weight. Prey discovery is mediated by a size-dependent search rate. The ingestion and assimilation of food leads to growth of individual fish, which is then represented by moving fish to a larger size class. Mortality is due to predation and intrinsic size-dependent mortality, and then at the same time there's a fishing mortality imposed on the model, which applies to any fish bigger than 1.25 grams. In addition, the physiological rates here increase with temperature according to an homogeneous relationship. And this the model is largely based on a model published by Blanchard et al. In 2012, if you're interested. The other type of model that was used is the dynamic bioclimatic envelope model by William Chang. And this is based on the current distribution of key commercial species. So while the dynamic size spectrum model doesn't have species information and treats everything as one, here you have direct information for key species. It has an index of habitat suitability based on temperature, bathymetry, salinity, sea ice, and specific habitat conditions. It has an aerobic scope from temperature preference profiles. It uses population carrying capacity as a function of unfished biomass, habitat suitability, and primary production. And it describes a characteristic weight for each species as a function of temperature and oxygen. And changes in relative abundance and biomass are based on population carrying capacity, population growth, and advection diffusion of larvae and adults. So this is roughly how these two models work and are designed. If we take a look now at what happens in the environmental conditions that we've been investigating in between the two scenarios. So these pictures that you see here are for the end of century conditions, so to 100. And we're taking a look at how much the conditions changed over the coming century for the mitigated scenario on the left-hand side and the unmitigated scenario on the right-hand side. And you can see that for temperature, there's a pretty clear tendency pretty much all over the globe to increase by a couple of degrees for the mitigated scenario and by 3 to 4 degrees in the unmitigated scenario. This is pretty homogeneous. It's only in the Antarctic that increase is pretty low, and some episodic, some small islands that actually have shown increase here. What we're looking at is the median of the ensemble used. So this is what represents the average state here. At the level of phytoplankton concentration, surface concentrations, you have a much more heterogeneous picture, especially for the mitigated scenario. You have generally a decrease in the tropics and in most of the continental margins. You have a couple of islands and a couple of areas in Oceania and Southeast Asia that show an increase actually in concentrations for the mitigated scenario, while for the unmitigated scenario, the situation is much clearer. There's a general decrease pretty much all over the world. Again, my only exception is the Southern Ocean here. If you look at zooplankton, that looks pretty similar to what happens to the phytoplankton, so the one trophic level below. There's only a couple of exceptions where things change, like some of the Southern Ocean islands. But generally, the picture is pretty similar to phytoplankton, with decrease in most of the areas of the world and only very few areas of increase for the unmitigated scenario. So if then we take a look how that affects the potential catch change in the two models, we now have, this is all for the mitigated scenario. And we have the bioclimate envelope model on the left-hand side, and we have the dynamic size-based model on the right-hand side. And we can see that the decrease in phytoplankton pretty much translates to a decrease in potential catch in most of the areas. Particularly, we have a decrease in the tropics and in part of the Southern Ocean. And we see quite good agreement between the two different model systems for the fisheries catch, with the exception of the northern high latitudes, which are quite different, which is also where the biggest uncertainty in the environmental variable sits. So that is only to some degree surprising, as they have also different dependency in the environmental variables. The areas most affected, as mentioned, are the tropical ocean, but also the Northeast Atlantic is consistently strong affected by the decrease in fisheries catch. And we shall now take a closer look at how this is coming out from the system. So what are the ways of propagation of the climate change signal, and what is the significance of changes that we have obtained? First, let's summarize what we've seen from these pictures so far. So the EEZs that show the largest decrease in potential fish catch by the end of the century are in the tropical countries, mostly in the South Pacific regions. Also, the Northeast Atlantic is likely to decrease already in the midterm. High latitude regions are generally more variable and showing less decrease or even increase. Some caveats to the simulations, as I started to hint before, the ESMs may have substantial biases at the local level, particularly near coastal areas, and don't cover phenomena that are triggered by mesoscale dynamics. The range of response to climate change in the Earth systems models is considerable. The applied large living marine resource models don't include adaptation. The size spectrum model, to some degree, doesn't need it because it doesn't have species, so there's no species that can adapt, but still there is no mechanism for adaptation in it, and no higher trophic level feedback on the climate system is included in these studies. So it's a one-way feedback of the climate on the fisheries catch and not from the fish on the climate. The scenarios represent a hypothesis only of the greenhouse gas emissions. They don't include mitigation strategies at the level of individual countries or local policies. So if we then try to figure out what is actually driving the changes in the fish catch potential, already from the agreement in a substantial amount of areas in between the models, we can conclude that the changes are likely to be driven mostly by the phytoplankton, the resource productivity. So this is because both models are affected by temperature, but they differ in their implementation of temperature. The bioclimate envelope model affects the temperature affects the fish distribution, growth, body size, and mortality, while in the size spectrum model, it universally affects the physiological rate. So for the size spectrum model, the temperature increase does not have a uniquely positive or negative impact on stocks or catches. Accordingly, it's likely that the decrease we see is actually caused by mainly by the decrease in resources and not by the increase in temperature. And we have done a sensitivity experiment. This is a slide from Jon Bruggeman, who provided this, where you clearly see that in 3 different chains of simulations. On the left-hand side, you see a simulation where only the prey change was imposed on the model. In the middle, you see one where the temperature change was imposed, and then in the on the right column, you see the combination of the two, and you can clearly see that the combination, so the full picture, is pretty much given by the change in prey only, and only to a small degree the variability comes from the temperature change. Let's take a look at how significant this change is at the different trophic levels. So we can define a signal-to-noise ratio, where here we use a definition of signal as the median relative change at the end of century with respect to the median present day, and the noise as the probable error, so the mid-range of individual model responses and change signal at the end of the century. So this is similar to approaches in other studies, but usually the signal in most of the studies is similar given as the change at the end of the century or mid-century, while the noise is often given as interannual variability. We have not used that here, but we have used the range within the ensemble because it's in the end the ensemble uncertainty we are most interested in. And also we have not used the standard deviation, as we didn't find that sensible in the given the size of our ensemble, which is pretty small. So we've used the mid-range of the individual model responses and changes with respect to the change signal at the end of the century. And then you can build a ratio of these two. And if this ratio is 1 or bigger, then you can generally conclude that the signal is at least as big as the noise. So you've got significant change, and if not, then it's not so significant. So if we take a look at these figures, on the left-hand side, you find histograms of all the different EEZs weighted in the same way. And for the variables of temperature and phytoplankton here. On the right-hand side, you find maps of the significant changes across the globe. What you can see is that the distributions are already hugely different. So for temperature, you have a clear significance for essentially all of the areas, with, again, the exception of the Antarctic, which stays insignificant. While for phytoplankton, it's much more mixed. You have a majority of areas that are significant, which is good, but you have also a significant amount of areas that don't show significant change, where the noise is quite big. And you can see that the most significant changes in the phytoplankton you will find attached to the continental shelf, and in Southeast Asia on the archipelagos, and some islands in the Pacific. But you have lesser significance in other islands in the southern Atlantic and southern Indian Ocean, and also some of the Pacific islands are lesser significant. And you again have the problem of the higher latitudes in the northern hemisphere. Distributions for zooplankton and fish catch are quite similar to those of phytoplankton. So the significance of change propagates pretty consistent through the system. You find the same patterns either in data distribution, either spatially. There's only a few variations of details in some of the islands, and we shall take a look in the next analysis what may be beneath these minor differences in propagation from phytoplankton over zooplankton to fish catch. Here's again an overview over the 4 different variables, and we can confirm that the changes between phytoplankton, zooplankton, and fish catch are quite similar compared to temperature, which has a much larger significance of change essentially all over the globe. So if we want to take a look at how the actual signal propagates through the food web, we used here the concept of trophic amplification. So amplification here is defined as a relative change in a predator over the relative change in food. So when the absolute value of this ratio is bigger than 1, then we have an amplification of change. When it's smaller than 1, we have an attenuation. When the amplification is bigger than 0, we can assume that it's the bottom-up mechanisms that drive the change, because they have the same sign. If they are lesser than 0, then you can assume some top-down control. So the predator increases when the prey decreases, by decreasing the prey by eating it, or other way around. The prey increases because there is a decrease in predator. Here we applied this indicator over the whole modeled food web. So we went from the potential fish change, catch change, to the resource, to phytoplankton at the lowest level. And we got the following pictures. So on the left-hand side, you have the distribution of the different amplification factors. On the right-hand side, you have, on the x-axis, you have the change, so the decrease in resource, which is phytoplankton. And on the y-axis, you have the amplification factor, or the amplification ratio, better. And you can see that the distribution is quite different between the two. So y for 2.6 for the mitigated scenario, it's rather vertical. So there's less variability in the decrease of phytoplankton, and there's things tend to group around that small decreases with a wide range of amplification factors, while for the unmitigated scenarios, you can see that for a large number of large decreases, you have consistent factors of bottom-up controlled attenuation or amplification in relation to where you are. So if we then look at the spatial distribution of the two, you can see where the potential fish catch actually is most affected by the change in resource in phytoplankton concentrations. And this, to some degree, is an indicator of the vulnerability in the system. So where the fish catch is very potential, is changing very much with the change in resources, this is an indicator for a vulnerable system, while if the fish catch potential doesn't change much with the resource change, then that system is more resilient to change. And you can see that most of the areas where we had significant change and where we also had the largest changes, which is the tropics, are affected strongly by the change in resources. So these systems are quite vulnerable. There's a couple of systems that in between 2.6 and 8.5, so in between mitigated to unmitigated change, actually change sign in their sensibility of the to the resource change. So while under mitigated conditions, they tend to be top-down controlled, they switch to bottom-up control in the unmitigated change. So this is true for these island chains in Southeast Asia, and also for some archipelagos in Oceania, in the Pacific. So if we summarize what we've seen during this webinar so far, and which is where we're going to stop, the two climate living marine resource models consistently predict an overall decrease of potential catch. There's substantial heterogeneity in environmental conditions and potential catch across the EEZs. Changes under unmitigated conditions are mostly significant, but locally uncertainty may exceed the signal. Largest and most significant changes are generally in tropical countries and in the South Pacific, and also in the Northeast Atlantic decrease is significant. The high latitudes are more uncertain. Impacts on catch are strongly driven by changes in primary production we have seen. And tropical and subtropical EEZs dominantly amplify the decrease at lower trophic level, rendering them particularly vulnerable, while areas with increased productivity tend to top-down control change patterns. As the overall conclusion and take-home message of this webinar, we can say that increased carbon emissions are likely to reduce the global fisheries catch potential. And with that, I thank you for your participation and following this webinar. Again, here's my email in case you want to get in touch, and I'm waiting for your questions.
Wow, thank you so much, Momme. Very interesting talk. And in fact, I invite all the attendees, there are more than 100 attendees, and a little bit more than that. So please ask your questions, because there's a panel on the bottom part of your monitor, so use it. There's some question arriving already. I wanted just to open the question section by asking you something about the modeling part of the story, in the sense that you say that you have been using climate models from CMIP archives. There are many of those, so I wanted to ask you, how did you pick up those that you used in your ensembles for having your results?
Okay, so the choice of ensemble members for the driving environmental conditions of the fish models was given essentially by the requirements of the fish models. Mm-hmm. So while the dynamic bioclimatic envelope model has the necessity of having information on various variables like salinity, temperature, pH, primary production, and oxygen, so it needs models that provide all these variables. At the other side, the side spectrum model needs some information on the metabolic slope of the plankton community structure. So these conditions led to slightly different ensembles. In the end, we had pretty much ended up with the same ensemble, except for one member that is in the size spectrum model that is not in the bioclimatic envelope model, and other way around. That leads to these different requirements lead to slightly different ensembles used for the two cases. But again, we've looked at the environmental conditions and they are consistent in between the two, so there's not much difference there.
Mm-hmm.
What's different is the sensibility of those models to the environment. And that's why it was surprising that the two models, or a good surprise, that the two models have quite similar results over large areas, because they have very different parameterizations of the environmental dependencies.
Yes, that's very interesting. So I would have other curiosities on the model side of the story, but I see that there are interesting questions arriving from the public and the attendees. For example, this Phillips, Freedom K. Phillips is asking, given the information, what type of legal policy responses should be adopted, according to your opinion, Momme?
I don't think any legal policy responses should be directly framed based only on this piece of information. This piece of information gives a general overview over the globe, over the tendency of potential fish catch. But already in the report I mentioned, there are regional chapters which have much more specific information for individual countries. And then there's more information out there beyond this work. So I think legal policy should be based on a wider range of sources, of which certainly this work can be a piece. But I've mentioned the caveats, so you need to back that up with more information.
I see. There's another question arriving from Liudas, Griga Lunas. I don't see the affiliation, so please I ask all the members to add their affiliations so that we can say where are they from. And he asks, I have heard that the ocean currents have a large impact on plankton. Have the models taken into account changes in the ocean currents due to changes in the ocean temperatures?
Yes, absolutely yes. So these Earth system models that that I was introducing model the whole system. Yes. So they have atmospheric physics, they have atmospheric chemistry, they have the land ecosystem, and they have the ocean dynamics. So the ocean currents, ocean temperature, ocean salinity, and these ocean physics drive the marine ecosystem component and other vectors for the changes that you find in phytoplankton and zooplankton. So it includes either on the physiological level the increase in temperature. So the temperature is going to affect the growth, mortality, and all other physiological rates of the ecosystem model. But at the same time, also, it drives changes in stratification, in mixed layer depth, and in currents themselves. And those obviously affect the distribution of the phytoplankton and the resources for phytoplankton, which are nutrients, which tend to be locked up in the deeper ocean.
Oh, I see. I'm reading. There are other questions arriving. That's great. What is the most likely average percentage decrease of catch potential and or of the real catches by the end of the 2100th century, 21st century, under the RCP 8.5? This is Patrice.
Okay. Let me just quickly check that I give you the right numbers. But I think I had it in key messages, actually. So on average, the potential catch change is projected to decrease by 2.8 to 5.3% and 7 to 12.1% by 2050, relative to RCP 2.6 and RCP 2.8. So these numbers are going to increase by 100. I've currently got the numbers here for mid-century, so I hope that is an answer so far. I would have to look the precise percentages up, but they're significantly higher by end of the century for RCP 8.5. RCP 2.6 doesn't change much from mid-century to end of century.
Good. So there's also Mark Payne asking, Momme, what assumptions did you make about nutrient and turn-off scenarios in coastal systems into the future? And he says, am I right in assuming that this will be very important for the shelf systems?
Yes, they would. So this is one of the limitations of the study that I mentioned earlier, that we currently are using Earth system model projections. So the nutrients we find in these projections for these simulations. So if you want specific simulations for these near coastal fishery areas, you would have to go for regional models that include riverine loads and changes to them under future condition, which again brings you to another level of policy mitigation policy, not of climate change in this case, but on anthropogenic change, which is not included in this work. We are dealing with climate change here. So
there's another question from Professor Muranlai, RMSI, is asking how sensitive the results will be to the glacial melt from land-based ice, particularly in Bay of Bengal.
Can you repeat? I didn't get that. From the?
Yeah. How sensitive the results will be to glacial melt from land-based ice, particularly in the Bay of Bengal.
I have not studied the Bay of Bengal in detail myself. Certainly the impact of glacial melt are included as far as they are resolved by the Earth system models. So again, I haven't looked in detail what the changes here are in the specific Bay of Bengal. We could certainly look at it. If you look at the report chapter, we have detailed numbers for each individual EEZ in there, which you can take a look at, and that would provide the change that as it is projected now by this set of ESMs, which to be honest, I'm not entirely sure how reliable they are for the glacial mating at the Bay of Bengal.
So thank you, Momme, for this answer, also because it takes into account a little bit of the other questions that are arriving, and that they are very punctual in terms of asking particular parts of the planet, meaning that there are, serious implications at the local level. So maybe we can grasp as the last question, this one that I find very interesting from Samir Bhattacharya. Now is not connected anymore, but you can see maybe the reply. Looking at when we will post this video. I will read it because it's very, very good. It says, Samir, I'm from CUTS. CUTS is the Consumer Unity and Trust Society International. And he says, we work with fishermen at the grassroots level in various parts of the world, including India, Ghana, Kenya, etc. Can you tell me what are the key lessons that can be taken at the community level from this information? And listen to this. Me being the bridge between who have access to this high-level work, backed by technology, data, etc., and those who haven't. Thanks.
Okay, so as I said, this chapter in particular is giving a large-scale overview of what's happening to the system. What it gives at the community level as a piece of information is certainly an indication as to what impacts in your area you may expect. So in relation to where you are, these are more or less reliable, as I mentioned during the talk. If you are in the tropical countries in the Pacific, if you are at the Northeast Atlantic, there's quite a degree uncertainty on the fact that catch is going to decrease substantially. Then again, you would have to back that up with other information, which is more species specific, to understand what that means, particularly for your case, because I assume a fisherman then maybe bivalve fisher, or maybe go fishing at high seas, may go for coastal fishes or demersal fishes, and there the impacts may differ largely. So you need to back that up with more information again. But at least you get a general indication what you can expect for your area.
Yeah. So thank you, Momme. I think that now, time is almost over because there are other questions arriving, so maybe you can answer them directly. I will post that to you. In order to close the meeting, maybe we can just show the very last slides. I would like to remember.
Oh, yes.
sorry, I want just to remember the next, go to the next slide, this one, because there's another webinar concerning agriculture between CMCC and FAO. This will be in October 3rd. And if you would like to have more information, please have a look to the website of CMCC. And then I think more or less you have a last slide, maybe, Momme, no?
Yes.
Yes. So this is just to say thank you. Thank you, Momme, in particular, for this very interesting talk, giving rise to, you see, questions from the viewpoint of modelers and science, in a sense, and others that are very applied for people who are really working in the fish catch areas. So thank you all for attending the CMCC webinar, and this will be posted soon on the website of CMCC. So goodbye, everyone, and see you to the next webinar. Thank you, Momme.